I'm Hao. Today I'm going to introduce our work entitled Exploring the Mechanism of Polypharmacy Side Effects in Two-Stage Graph Neural Network. And in this work, we developed an XAI framework called APRILE for discovering side effect mechanisms caused by drug combinations. Let's start with introducing the APRILE framework. Actually, the figure is composed of two modules, APRILE predictor and explainer, for predicting and explaining, respectively. They share the same graph neural network architecture, but have different trainable parameters and object functions, so they can be regarded as two stages of a graph neural network. APRILE predictor learns the drug representation from a pharmacogenomic knowledge graph. The knowledge graph includes drug target, functional associations, or physical connections between or within drugs and proteins. The knowledge is firstly extracted by the protein representation module, and then it is passed from protein to learn drug features by the drug representation module. These two modules both contain multiple layers of graph convolutional neural network. And finally, the prediction module takes these learned drug embeddings as inputs and predicts all possible side effects. And in this module, we use Bismuth tensor factorization as the multi-label classifier. The examiner produced a tentative molecular mechanism level explanation to boost prediction. Given side effect predictions, APRILE explainer generates a subgraph of the original knowledge graph that are most influential for the predictor, and then we investigate the functional roles of proteins in the explanation with goal enrichment analysis. In effect, the original graph neural network and graph explainer cannot account for multiple mechanisms by which polypharmacy can cause side effects. For example, drug having opposite side effects, but acting on the same target protein or enriching effects through the sequential effect. So to overcome this limitation, we developed the lazy training strategy. And by using lazy training, APRILE is able to different side effect mechanisms by stressing the learning of all kinds of relations on the knowledge graph that weaken the learning on the drug and protein attributes. And based on this, we designed two metrics to describe the effective complexity of the polypharmacy side effect mechanisms, the Q and CPU scores. They quantify how important the information on drug targets and non-target proteins is respectively. They also have to adjust the contribution of the proportion of drug targets and non-targets during the expanding process. And now we have talked about our method. Let's move to the experiments and results. We built APRILE on the pharmacogenomic knowledge graph involving 1.5 million relations among 284 drugs and around 90,000 drug targets and non-targets, and tested on the around 4.6 million drug-drug interactions. Here's the results. In order to ensure that the APRILE performance is balanced on the seen and unseen drug-drug interactions, the predictor model selection is based on the generalization. The selected prediction model is trained with 90% samples and has the most balanced performance on the training and the remaining 10% of testing sets. And besides, we find that the predictor learns meaningful side effect embeddings. Actually, in the right figure, a two-dimensional U-map projection of side effect embeddings learned by the selected predictor and contains meaningful factor for tainted disease categories and symptoms, and also the mental disorder. As mentioned earlier, we show the example of predicting the side effects may cause the combination, may caused by the combination of drugs. In explaining why model makes these predictions and for evaluating them, we use APRILE to generate such explanations for dozens of side effect drug pairs in one. And here's the part of the result. We performed a lecture-based evaluation on the explanation's reliability, and literature evidence was found for explanations for these top predictions. And actually, in the paper, we found evidence for 2x3 genes for SCOSMA and targets and non-targets for other cases. And besides, more literature-based evaluation results and quantitative analysis could be found in our paper. We are welcome to check. To investigate the role of the laser training in predictor, we do the ablation study on it. The right figure shows the result. This trade-off between model prediction accuracy and the PPU score for each data set. And we found that laser training improved the explainability of APRILE predictor stably without significantly reducing model prediction accuracy. And now let's move to the polypharmacy side effect classification. Very few systematic methods are available for this part. To address this challenge using APRILE, we constructed a polypharmacy side effect feature matrix based on the explanation and applied the frequency of propagation, and finally obtained the 25 side effect clusters in total, and we found some mechanism association behind them. Here we also want to show APRILE generates new insights into molecular mechanism of polypharmacy side effects. By using a medical expert can exercise polypharmacy risk more accurately and efficiently, and we case study for our category of the side effects like infection, metabolic disease, gastro disease, and mental disorder. And this table shows the mechanism generated by APRILE in these case studies. And in conclusion, we present a first step toward AI-guided polypharmacy side effect explanation. And using massive data that already exists, APRILE has generated model-driven hypotheses for these mechanisms. Thank you so much for listening, and you're welcome to contact us by email. I'm happy to answer any of your questions. Thank you.